Welcome back to Applied Mathematics. In this video, I want to review some concepts related to multiplication and division. As we've done in previous videos, I'm going to go through talking about how to multiply and divide exact values, how to multiply and divide approximate values, how to multiply and divide some algebraic expressions. Although in the last one, there's a lot you can do with multiplying and dividing algebraic expressions, some of which we will be talking about a little bit later on in the course. All right, let me get my head out of the way. We will dive into this, starting off with the rule for signed numbers. One of the things I like about signed numbers is that the rules for multiplication and division are exactly the same. If you have two numbers with the same sign, the result comes out positive. If you have two numbers with different signs, the result comes out negative. The same is true in multiplication as in division. And that's actually one of the places where I think it's most important to remind you. You can put a negative sign in the numerator of a fraction, or put a negative sign in the denominator of a fraction, and either way, the result will come out negative. But if you try to put the negative sign in both numerator and denominator, then your result is going to come out positive. So keep that in mind. You can sometimes write a fraction with a negative in front. Sometimes it's more useful to put that negative in the numerator. And while it's almost never useful to have the negative sign in the denominator, you can always go in the other direction and move it to where it is useful. But if you try to put a negative in the numerator and in the denominator, well, you've just completely defeated your purpose and you could have just left it off entirely. Speaking of fractions, that's where addition and subtraction start to diverge. If I want to multiply, two fractions together, the rules tell me that I want to multiply across the numerator and I want to multiply across the denominator. And I chose this example specifically because even though 12 over 25 and 35 over 32 do not reduce, once you've started multiplying things together, you might notice that we have 25 here, which is 5 times 5, and 35, which is 5 times 7. The common factor, one of the 5's cancel out, leaving a 7 in the numerator and leaving the other 5 in the denominator. Then you have 12 and 32. 12 is 4 times 3, and 32 is 4 times 8. The common factor of 4 cancel each other out, leaving you with the 3 in the numerator and the 8 in the denominator. And 3 times 7 over 5 times 8 is definitely an easier expression to evaluate. 3 times 7 is 21, 5 times 8 is 40, and there is nothing else we can do to reduce that fraction. Once again, this is a process that is going to be very important to us a little bit later on in the course once we start throwing variables in the mix. So for example, I might have x over 7 multiplied by 15 over 2x. And in this case, the common factor of x between the numerator and denominator cancel each other out, leaving me with 15 over 7 times 2, 15 over 14. All right, so even though, yes, your calculator can do a problem like this for you, you don't have to be able to do it by hand. When you get to a problem like this one, that's where your calculator is going to start panicking and you have to know what you're doing. I have always found that taking the time to practice on these, even though your calculator can do them, they're the easy ones. They're the ones that you can do fairly simply by hand. They're the ones you can check your work on a calculator. So make sure you know what you're doing on those before you get to the hard ones. Dividing fractions. I'm just going to give the general rule here. I'm not going to go through a numerical example. But if we have a fraction a over b divided by another fraction c over d, we can rewrite that as multiplication. The fraction on the left stays alone, the division turns into multiplication, and then you take the reciprocal of the fraction on the right, flip it upside down. From there, you can reduce if necessary, the same way we were doing before. All right, that's fun and exciting. One of the interesting things that I really wanted to talk about here, though, was multiplying and dividing with algebraic expressions. And the rules I'm going to be looking at here pretty much all fall under the category of the distributive property. Remember, the general rule for the distributive property says that if you have some number a multiplied by some addition, b plus c, you can distribute through and call it ab plus ac. Well, that works perfectly fine if you have something like 7 times the quantity, 2x plus 3, giving you 14x plus 21, right? 7 times 2x, 7 times 3. That also works if you have division. Now, this is where things get a little bit tricky, because if I have something like 9x squared minus 6x all over 3x, I can rewrite that as 1 over 3x times the quantity 9x squared minus 6x. Right. I want to take a moment and stress here. Because I have subtraction in the numerator, things are going to work fine. If I had subtraction in the denominator, this would become a lot more challenging. We'll talk a little bit more later on in this course about what a lot more challenging looks like. But by writing it out in that form, you can see that we can use the distributive property. And I would never write out this step. I would just jump right ahead to distributing, splitting the fraction up and calling it 9x squared over 3x minus 6x over 3x. 9 divided by 3 is 3. X squared divided by x is x. 6 divided by 3 is 2. X divided by x is 1. Multiplying by 1 doesn't change anything. So there we have it, 3x minus 2. When you are dividing, you can have addition and subtraction in the numerator, but you have to have a single term in the denominator, again, or things get messy. When you're multiplying, it turns out to matter a lot less. If you have a single term multiplied by stuff being added together, then we're fine, as we saw before. If you have stuff being added together in multiple places being multiplied together, it still works, it's just messier. So if I have something like 2x plus 3 times 3x minus 5, I can still use the distributive property. 2x times 3x is going to be 6x squared. 2x times minus 5 is going to be minus 10x. 3 times 3x is 9x, and 3 times minus 5 is minus 15. Combining some like terms in the middle, and we end up with 6x squared minus, well, it would be minus 1x, but again, the 1 doesn't do anything, so we don't write it out. 6x squared minus x minus 15. If I have more than just two terms, this still works. Although once you start getting more terms, that's where notationally things start to get a mess. So here's a trick that I like to use. So I have x squared plus 3x minus 5 times 2x squared minus 9x plus 4. All right. The trick that I'm going to use here relies on my polynomials here each being complete. By complete, I mean I have an x squared term, I have an x term, I have a constant term. A polynomial that is not complete might look something like x cubed minus x plus 7. We have an x cubed term, we have an x term, we skipped the x squared term. If you skip the x squared term, the process I'm about to show you won't work. You can solve that problem by writing it in anyway. X cubed plus 0x squared minus x plus 7. And if you take the time to do that, then the process will still work fine. All right, but let's get that out of the way and let's get back to solving this problem. So what I'm going to do is in the first polynomial, I'm going to work term by term. Let's make that circle a little bit smaller so my plus sign doesn't get lost. But I'm going to take x squared and distribute. X squared times 2x squared is 2x to the fourth. X squared times minus 9x is minus 9x cubed. And x squared times 4 is 4x squared. Now I'm going to go to the next term. When I write this out, instead of just continuing on the same line, I'm going to go down to the next line and I'm going to move over one space. So that when I take 3x times 2x squared, that's going to give me 6x cubed. And if I put it here over one space, then my x cubed terms line up with each other. And it's going to make combining like terms to simplify a lot easier. It will always work out that way. 3x times minus 9x is minus 27x squared. 3x times 4 is 12x. Then for the minus 5 term, again, down to the next line, over one space. Minus 10x squared plus 45x minus 20. Add up, combining like terms, which are already lined up for you down the columns. We've got 2x to the fourth. We've got minus 9 plus 6, all told that's minus 3x cubed. We've got 4 minus 27 minus 10. That's minus 33 all told, x squared. And then we will have 57x and minus 20. All right, there we have it. On to my favorite here, the accuracy rule. When multiplying or dividing approximate values, round the calculated value to match the worst accuracy of the initial measurements. So here again, the whole idea is what was your weakest link? What is holding you back in the calculation? And the particular example I tend to think about with this rule is just a simple area problem. All right, so let's say that we are trying to calculate the area of the rectangle. We measure the length of the rectangle. Actually, I'm going to write this the other way. We measure the width of the rectangle using a highly precise micrometer because we have a micrometer that fits. And we get that the width here is 1.278 inches. And then the length of the rectangle is unfortunately too big to fit in the micrometer, and we don't have a larger micrometer, so we have to use a different tool. And so we use a simple ruler. And the simple ruler tells us that the length here is 3.37. inches. We've lost precision. Our length is measured to the nearest hundredth of an inch. Our width is measured to the nearest thousandth of an inch. Because we lost precision with that length, that's going to cause problems as we go forward, but not too badly. All right. If I bring my calculator back, and let's turn on some more lights so that we can actually see the calculator. There's the calculator. And I multiply 1.278 times 3.37. My calculator tells me that the measurement in this case is 4.30686. But we look at our accuracies. 3.37 has 3 significant digits. 1.278 has 4 significant digits. The worst accuracy was 3 significant digits, so I want to round this to have 3 significant digits. That's going to be 4.31. And that will be in square inches, right? Inches times inches is square inches. In this particular case, the precision, nearest hundredth, matched the precision here, nearest hundredth. That is entirely a coincidence. I will tell you it happens about 50% of the time. About 50% of the time, it's off by 1. That just is a matter of how big your numbers are and where that's going to fall. I forgot to turn that light back off so that it wouldn't glow under my armpit. There we go. All right. But matching the precision is nonsense in a case like this, right? This is the nearest hundredth of an inch. This is the nearest hundredth of a square inch. An inch and a square inch are not the same measurement. They're not measuring the same kind of thing. Talking about precision in terms of one or the other is, well, frankly, nonsense. That's why we need a rule like this. All right, so the same idea holds for multiplication and for division. And again, it's very useful here because the precision doesn't make sense, right? Precision is nonsense. We're comparing apples to oranges. Things have different units of measure. That becomes even more apparent if we look at a division problem, like a rate of change. All right, so let's say that we have traveled 327.5 miles in 2.8 hours. All right, because we are comparing apples to oranges, the relative precisions of these things are nonsense to compare to each other. But to find the rate of speed, I know, calculate the speed that you're traveling, you take the distance you went, you divide by the time it took, you ask the calculator to do all the hard lifting for you. So 327.5 divided by 2.8. And when I do that calculation, I get this value, 116.964, etc., etc. My weakest accuracy was my time, 2.8 hours, had 2 significant digits. So I want to round this value to 2 significant digits. That's going to come out as 120 miles per hour. Right? Remember, Zeros at the end of a number that don't have a decimal point are not treated as significant zeros. This is why that's so important, because we don't want that zero to be significant. We need it to round to only have 2 significant digits. All right. But there's our basic concepts of the accuracy rule for rounding multiplication and division problems. I hope looking through that feels familiar to you. All of the multiplication and division rules for exact values for polynomials, certainly also hopefully things that you are remembering from previous mathematics courses. With that, I think I'm going to wrap up on this one. Thank you as always for joining me. I'll see you next time.